Hello, Mr. Betts here. I want to take a look at a couple examples where we want to answer questions about the graph of a function. So the first one here, we're just analytically given f of x. So f of x is this function here, and we want to know on what open intervals is f of x decreasing and concave up. So remember, decreasing, we're going to be looking at the first derivative, and specifically we're looking for where the first derivative is negative. And then for concave up, we're going to be looking at the second derivative, and specifically where the second derivative is positive. So what I'm going to do here is I'm going to take the first derivative, find critical points, and make a sign chart. And then I'm going to take the second derivative, I'm going to find critical points and make a sign chart. And I misspoke there. I'm not going to find critical points, but I'm going to find potential inflection points. So let's start with the first derivative. So first derivative is going to be 6x squared minus 18x plus 12. Then we want to find critical points because that's where the first derivative could equal 0, and then also where the first derivative could change signs. So I'm going to factor out a 6 and factor. So we get critical values or critical points at x equals 1 and 2. So now I'm going to make a sign chart for the first derivative. And at x equals 1 and x equals 2 is where the sign of the derivative could change. If I plug in a number to the left of 1, say 0, I'm going to get a positive times a negative, which is going to be a positive. If I plug in a number between 1 and 2, I'm going to get a positive times a positive, which is negative. And a number bigger than 2, I'm going to plug in and get positive, so that's going to give us a positive. So the first part of the question here, the function is going to be decreasing on the interval from 1 to 2. Notice for decreasing, so decreasing and increasing, we do include the endpoints. In the end, we are going to just make it an open interval. We won't include the endpoints, but if the question was strictly increasing or decreasing, we should include those endpoints. Now for the concavity, we're going to take the second derivative. That's going to be 12x minus 18. We want to figure out where that could change signs. We're going to call those points, instead of critical values, we're going to call them potential inflection points. So we set that equal to 0, get 12x equals 18, and x equals 3 halves. So I'm going to make a sign chart for the second derivative. I think these sign charts really emphasize the importance of labeling. So if we have two different sign charts, we need to make sure we know what those two different sign charts represent. So this one is going to represent the sign of the second derivative. If I plug in a number to the left of 3 halves, like 0, if we plug in 0, we get negative 18, so that's negative. If we plug in a big positive number, then this is going to dominate here, and we're going to get a positive. So the second derivative is positive. That's what we're looking for here for concave up on the interval from 3 halves to infinity. So to answer this question, then we need to put those two things together. So the answer then is going to be, so f is decreasing and concave up on the interval where these two overlap, which is going to be from 3 halves to 2. And remember, we're going to make it an open interval because that's what it's asked for in the problem. In the second example here, we don't have any analytical information. We're only given graphical information. And so one important thing is that this is the graph of f prime, but we're answering a really similar question. So the question here says, where is f of x decreasing and concave up? So remember, decreasing is where f prime is negative. All right, so on this graph right here, the function itself will be decreasing where the derivative is negative or below the x-axis. So the function is going to be decreasing from on the interval from b to d. Now, concave up is a little bit trickier. So concave up, normally we would take the second derivative and look for where that's positive. We can't take the second derivative of a function or a derivative that we don't know. So what we're going to have to do is infer from the graph where f double prime is going to be positive. And remember that the second derivative is the derivative of the first derivative. So where f double prime is positive is the same thing as looking at where f prime is increasing. Because if f prime is increasing and we take the derivative of that, we're going to get positive slopes on f prime, which gives us a derivative of f prime that's going to be positive. So from 0 to a, f double prime is going to be positive. That does not overlap with our decreasing interval, though, so that's not very useful. But it's also going to be increasing from c to e, and part of that does overlap. So it's concave up from, I'll include both of these for now, 0 to a and c to e. But where it is both decreasing concave up, it has to meet both of these criteria. So we're looking for where not only is the graph of f prime below the x-axis, but also increasing, and that's going to be the interval here from c to d. So f is decreasing and concave up on the interval c to d. If we were asked to justify our answer, we would say it's decreasing because the graph of f prime is negative, and it's concave up because the graph of f prime is increasing. So we can look at increasing and decreasing behavior on f prime to get information about f double prime.